So now that you guys have seen a few problems dealing with these probability rules of addition and multiplication, we can make the problems a little bit more complicated. The addition and the multiplication rule that you've just seen deal with really specific cases of just disjoint events or independent events, and those are actually really pretty rare. So now we're going to make the rules a little bit more general so we can deal with non-disjoint cases and dependent events. So to make the addition rule a little bit more general, we still want to add up two events. So if we want to know the probability of event A or event B, we can add up those two events. But if we're dealing with non-disjoint events, meaning they have an intersection and they can occur at the same time, then we have to subtract that intersection out once. And the reason for this is because we've added those individuals twice, and so we have to subtract them out once so that they're only counted once. So let me show you quickly what I mean. Here's a survey of students and what appliances they have in their college dorm rooms. They could have TVs or refrigerators, or they could have both. So having a refrigerator and having a TV are non-disjoint events because students have both of those in their dorm rooms, or just one. And so if we wanted to find out the probability that a randomly selected dorm room will have a fridge or a TV, we would use the general addition rule. So the way this works in this instance is that we're going to add up all the people that have refrigerators in their room. So the probability of selecting someone with a refrigerator is 0.39. The probability of selecting someone with a TV is 0.60. Now we've counted the people that have both a refrigerator and a TV twice, and so we're going to subtract those people out once, and they're 20% of the population, or a probability of 0.20. So the final probability, 0.79, is the probability that a randomly selected dorm room will have a fridge or a TV. So now we've made our addition rule a little bit more complicated because we've added this third term to it. We can no longer just simply add probabilities together. But again, if we're dealing with disjoint events, one that can't occur at the same time, the probability of A and B is going to be 0 for those disjoint events. And that's why that basic addition rule worked for only disjoint events. Now let's move on to the multiplication rule. Remember, the multiplication rule was for probabilities where we wanted to find the intersection, so A and B. We said that we could just multiply those two probabilities together, but this was for specifically two events that were independent. Now we're going to make it more complicated and allow our events to be dependent, and that's going to give us the general multiplication rule. So the general multiplication rule looks like this. If you want to find the probability of A and B, you're going to multiply two probabilities together. The first is just the regular probability of event A, but the second probability is what's called a conditional probability. So the probability that you see event B given that event A happened. So you know what happened in event A. It could also be notated like this, with event B going first and conditioning upon event B. It doesn't matter which way you write it, as long as whatever you put in this first term is what you're conditioning upon. Now, I recognize that you're maybe not familiar with conditional probabilities, so let's take a step back and remember that we dealt with conditional distributions before. Remember that conditional distributions were ones in which we had some information, and probability distributions are the same thing. So here we're writing this as the probability of B given A. So we know some information about A already, that something in event A has occurred. If this is a die roll, then we know what number came up on a die roll. If it's a coin flip, then we know what coin flip occurred. When we were dealing with conditional distributions before, remember that we looked at the passengers in the Titanic, and we specifically conditioned upon whether or not the passengers survived. And this gave us a different distribution as to what class members were in each class, first, second, third, or fourth. If we just looked at the passengers that did not survive, then this distribution would look different. Therefore, knowing whether or not the passenger survived or did not survive changes the distribution of class. And that's what it means to be dependent. Having knowledge about the survival changes the probability distribution or the conditional distribution of the class. So let me work through a few problems to show you how to calculate conditional probabilities and how they might read. So here we have a deck of 52 cards, and it's a standard deck, and you draw at random one card. Now I'm going to tell you what's on the card, but you don't know what the card is. Let's start by saying that the card is red. So that would mean, given that it is red, you want to know the probability that the card is a heart. So knowing that the card is a red card reduces the possible outcomes to 26, because there's only 26 cards that are red. And so that changes our probability that the card is a heart. There are only 13 hearts out of those 26 cards, and so only half of the remaining deck can be red. So the answer to this question is 0.5. This second question also gets at a conditional probability. So it asks the opposite. What is the probability the card is red given that it is a heart? So what the second question is telling you is that you have the information that the card is a heart. And so what is the probability that it is now red? So there are 13 possible hearts, and so we'll put that in our denominator. And in the numerator goes all the red hearts. And so there are 13 red hearts, and so the probability ends up being exactly 1. So the key to these problems is that when it says given that, that's what you're going to be putting in the denominator, are those possible outcomes. And the probability that the card is red, that's going to go in the top. So that's the conditional probability we're talking about when we're talking about this second term. We're multiplying a regular probability times a conditional probability because this information about what happens in event A is going to affect the probability of event B. And so this deals with our dependent events. Conditional probabilities particularly show up when we're dealing with sampling without replacement. So imagine you're drawing from a deck of cards, but you're not putting the card back. So you're changing the sample pool or the possible outcomes that are available. The other way the general multiplication rule is very useful is that we can rewrite the general multiplication rule in terms of the conditional probability. So we can find conditional probabilities using the general multiplication rule. In the next few set of videos, I will show you guys how to work through some problems that deal with the general addition rule and the general multiplication rule, where we're dealing with instances of non-disjointness and dependence, and show you how to solve those problems. Some of the problems are easier problems, but most of you guys have seen this before because you've taken Math 120 or some form of probability, so this stuff isn't particularly new to you.